Okay, next we're going to talk about chirality. And before we actually look at notes for that, I want to start by just going through some basic stuff. Okay, I'm going to draw for you, and I'm sorry because I really can't draw very well. But let's say that we had... I was going to go for mittens. I don't know that that's what this actually looks like. Let's say that those actually were mirror images of one another. So in other words, if you have a mirror right here, boop, 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 this would be the same on each side. I could take this and flip it over. And if I had drawn them both the same, they would be the same. Okay? However, if you take your two hands, they're mirror images of one another, right? Okay. And if I flip it over, what I find is I've got one that faces up this way and one that faces down this way. Okay, let's flip it over this way, and what you find is your left hand and right hand are not the same, right? Because they don't, what we call superimpose. That means that I can't put them on top of each other and they're not the same because of my thumbs. Now if you remove the thumbs, we can work with it, but not so much without having those thumbs there. So this actually makes a big difference in chemistry, and especially in the field of medicine and when working with biological entities. Okay, so let's look at two molecules here. What I've actually made for you is this. Okay, so it's a C-double-O bond, and we've got two CH3s. I haven't done the whole CH3 thing, but I guess I actually drew formaldehyde, which is more of like this. Okay. These two are mirror images of one another. Right? So they're mirror images. I can flip this, and wow, I can lay them on top of each other because they're the same, right? It doesn't matter if I do it this way, whichever way I want. They are the same. Okay, good. Now, let's get more complicated. What if I have instead a C, H, H, let's say a Cl and a CH3. Okay, the mirror image should be C, CH3, Cl, H, H. So I've got four things coming off that now. These two are the same. So we have three different things coming off there, right? So let's see. I'm going to go with that, and then I'm going to make its mirror image. Whoop. Right like that. You'll agree? Hope. Now, let me see. I can flip, and boom. They're the same, right? So we don't have a problem. They are superimposable, and that therefore we say they're not chiral, or they are achiral. So let me see. Let me reset this. And now I'm going to change things. Because I'm going to change one of these to blue. So let's say now we have fluorine here and here. Mirror images of one another, right? Okay. Now I'm going to flip, and I've got my blue and my white together, and look what happens. they're no longer superimposable. They're no longer the same. Sorry, it's hard for me to grasp these. There we go. These are the same. These are the same. Those two got reversed on us. That's the way it is. It's because these particular mirror images are not superimposable. And that's exactly what we mean by chiral. Now let me show you some notes that show something similar. Okay. These are mirror images of one another. They are stereoisomers, just as these two models were stereoisomers. They are mirror images of one another, but the exact arrangement in space of their atoms are different. So that the way that they're bonded to here is different. It's the same thing as your hands. The way that your thumb is attached to your hand is different on your two hands. And therefore they are stereoisomers, and each molecule we refer to as being chiral. This is a chiral carbon because it has 4 different things coming off of it. In this example, we've got 4 different colored balls coming off of that. The mirror image would look like this. So I want you to picture in your mind that you're rotating this. So in this case, here, let me see if I can do it. Hey, there we go. It actually works pretty well. That was not intentional. Okay, so if we rotate, I can put the blue one over here, right? Okay, you see that the green's in the back and the red's in the front? That's different from this one. So that's how we represent it on paper versus what the model kits look like. Since those are different, they are stereoisomers. The fact that they're mirror images of one another means that they're specifically enantiomers. Just to give you a little bit of preview, because we discussed this a little bit last time too. When we were looking at cyclohexane, I'm just giving you an example here. Make it simpler even. Cyclohexane is not flat like you think it is. If you have these two guys right here and you flip them, they move. Okay? Just a little side note, we'll come back to that later. Okay. Let's talk about Fisher projections now. Fisher projections, we've been looking at things so far like carbons in a chain, right? Let's simplify this a little bit. And we've been doing things like zigzaggies on purpose. Let me put back this guy right here. Because really, we've been looking at it from this perspective. Okay. Fisher projections instead look at things from above, and then they rotate it this way usually. And so when you have a Fisher projection, it is coming down this way. And the things that are coming off of carbon are going boom, 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 boom. Let me get that in the right orientation so you can see it clearly. And so when you do things like this, that crosshatch means that you're looking at it and you can see things right there that are different. So here's the Fisher projection of glyceraldehyde. We start the Fisher projection usually by putting a C-double-O bond for aldehydes and ketones up top. This guy, since he has 2 of the same thing on that carbon, 2 hydrogens, we don't need to worry about making a crosshatch for him because it's an achiral carbon. In other words, you don't have 4 unique things around this particular carbon. And this hash through here means that this is a chiral carbon. Now, when it comes to defining what type of arrangement of atoms you have there, if the OH is on the right, it is a D. The mirror image of that would look like this. I'm sorry, would look like this. That's just showing you a different way to write that, sorry. Which will look like this, right? Because your OH would go from this side to that side in your mirror image. Now, that OH is on the left, and we simply refer to that as L. Keep in mind, it doesn't matter if I say COH, C double bond H, all three of these, that's the same thing in different formats. Okay. Ooh, no it's not. I messed something up here, didn't I? I did not put an OH here. Okay, good. Now that's corrected. My apologies. What happens when you have a more complex example? So in this case, this would be a long aldehyde. We've got lots of hashes through there. Well, we've got 1, 2, 3, 4, 5 carbons, and 3 of them have stereocenters. I know that because when there's a hash, that means that that's probably a stereocenter carbon. Well, the name of this molecule would come from its arrangement of OH being this way, this way, this way. So you don't really need to worry about that unless they're one of the specific ones that you need to know. What you do need to know is whether or not how to name this guy. It's the furthest OH from the carbonyl that contributes to the name. So this OH is the furthest from that one. It's on the right, and that's why it's a D. This OH is furthest from that carbonyl. It's on the left, and that makes it an L. And that's how we determine D from L in enantiomers and Fischer projections.